A faint glow permeates all of space, a silent echo of the universe's violent birth. This is the cosmic microwave background, the oldest light we can see, a fossil from when the cosmos was a mere infant of 380 years old. By staying until the end, you will uncover 24 secrets hidden within this ancient light that redefine our place in the cosmos. We will explore how this afterglow reveals the universe's first moments, hints at other dimensions, and holds the ultimate answers to our cosmic origin and fate. What does the universe's oldest message whisper to you about the nature of reality itself? That faint glow is a baby picture of the universe. To understand it, we must journey back to a time before stars, before galaxies, when the cosmos was a searing, opaque soup of particles and energy. The universe was so hot and dense that light could not travel freely. It was trapped, bouncing endlessly from one particle to another. Then, after about 380 years, a monumental shift occurred. The expanding universe cooled just enough for atoms to form, allowing light to finally break free and stream across space. The cosmic microwave background is that first flash of liberated light, now stretched and cooled by the expansion of the universe over billions of years. It is the ultimate cosmic fossil. Its discovery was a stroke of serendipity. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, faint hiss in their giant horn antenna. They scrubbed away pigeon droppings and checked every connection, but the mysterious microwave static remained, coming with equal intensity from every direction in the sky. They had accidentally stumbled upon the afterglow of the Big Bang itself, a discovery that would earn them the Nobel Prize. This glow is incredibly uniform, bathing the cosmos in a chill of just 2.7 degrees above absolute zero. But its true story is told not in its uniformity, but in its tiny imperfections. Superimposed on that smooth background are minuscule temperature variations, tiny bumps and dips no larger than 1 part in 100,000. Imagine a perfectly smooth ocean surface, but with ripples so small they are barely perceptible. These tiny fluctuations are the cosmic seeds of destiny. They are the gravitational fingerprints of regions that were slightly denser than others. Over billions of years, gravity amplified these small differences, pulling matter together to form the first stars, the majestic galaxies, and ultimately, the planets that orbit stars like our own sun. Without these faint wrinkles in the fabric of the early universe, the cosmos would be a dark, empty, and structureless void. This ancient light is our most important map, and its subtle patterns hold the first clues to the universe's deepest mysteries, starting with the very instant of its birth. That faint hiss detected by Penzias and Wilson was far more than just background noise. It was the definitive proof of the Big Bang, the most compelling evidence we have that our universe was born from a singular, explosive event. This radiation is a direct echo of that violent birth, a snapshot frozen in time. To understand its significance, picture the moment of its release. For nearly 400,000 years, the universe was a searing, opaque fog, a plasma so dense that light was trapped, constantly bouncing between particles. Then, in a pivotal transformation known as recombination, the expanding cosmos cooled just enough for protons and electrons to combine, forming the first neutral atoms. This cleared the cosmic fog. Suddenly, after eons of confinement, light was set free. Those first photons, released in that brilliant flash, have been traveling across the expanding universe ever since, and we now detect them as the cosmic microwave background. The perfection of its spectrum is what seals the case. This ancient glow exhibits what is known as a perfect blackbody spectrum. It is the most precise blackbody ever measured in nature, its curve matching theoretical predictions with stunning accuracy. There is no known process other than the hot, dense origin of the Big Bang that could produce such a flawless signal. This cosmic snapshot confirms, beyond any reasonable doubt, that our entire observable universe was once compressed into an unimaginably hot and dense state, and has been expanding and cooling for the last 13.8 billion years. It is the ultimate validation of our cosmic origin story, offering a tangible connection to the universe's very first moments. Yet, this foundational secret only leads to a deeper, more profound question. What were the initial conditions, the very first spark, that set this magnificent and intricate process in motion? This first photograph of the universe reveals a cosmos of startling simplicity, yet one already imprinted with the blueprints for everything to come. The overall smoothness of this baby picture is its most striking feature, a testament to a surprisingly uniform beginning. But the story of our structured universe is written in the tiny deviations from that perfection. The minute temperature differences that appear as specks of red and blue on a cosmological map. These are the gravitational seeds of destiny. Each slightly warmer, denser patch created a tiny well of gravity, a cosmic pothole that began to pull in surrounding matter. Over billions of years, these small overdensities grew, snowballing into the first clumps of matter, then the first stars, and finally the majestic galaxies and sprawling galaxy clusters we observe today. A colossal structure like the Virgo supercluster, containing thousands of galaxies, can trace its lineage directly back to a specific, slightly warmer spot in that ancient glow. It is the ultimate origin story, written in the faintest of wrinkles on the face of a newborn universe. But this profound discovery raises an even more fundamental question. What was the cosmic force that so carefully planted those first, crucial seeds in the first place? Those tiny temperature ripples are not the only message imprinted on the cosmic background. There is a far more elusive signature hidden within its polarized light, a whisper from the universe's very first fraction of a second. This third secret is the hunt for primordial gravitational waves. These are not waves in water or air, but literal ripples in the fabric of spacetime itself, vibrations left over from the violent birth of the cosmos. Imagine the universe ringing like a colossal bell struck at the moment of its creation. The initial, deafening ring has faded, but a faint echo might still linger, a subtle warping of space that has been traveling for over 13 billion years. The theory of cosmic inflation suggests that in its first fleeting moments, the universe underwent an exponential, faster-than-light expansion. This incredible growth spurt would have been so violent that it sent powerful shockwaves through the very structure of reality, generating these primordial gravitational waves. Their telltale signature would be a specific swirl-like pattern, known as B-mode polarization, etched into the light of the cosmic microwave background. Finding this pattern is like discovering the unique fingerprint of inflation itself. The search has been one of the most challenging endeavors in modern cosmology. Initial, exciting claims of detection were met with intense scrutiny, and subsequent analysis suggested the signal might have been contaminated by interstellar dust. The hunt is far from over. New, incredibly sensitive experiments are now scanning the skies, designed to filter out all the cosmic noise and listen purely for this ancient reverberation. A confirmed detection would be a monumental breakthrough. It would provide our first direct observational evidence for inflation, allowing us to peer back into a time before the first particles even existed, into an era governed by quantum gravity. This would connect the vast cosmos we see today directly to the strange, subatomic laws that birthed it, offering a crucial clue in the quest for a theory of everything. But what was the ultimate source of these ripples? What quantum event in the first instant of time was powerful enough to set the very fabric of space-time trembling? Those tiny temperature ripples are far more than just cosmic static. They are a direct message from the quantum realm, a fossilized imprint of the universe's most fundamental uncertainty magnified to an unimaginable scale. In the very first instant of inflation, the empty vacuum of space itself was not truly empty. It was a seething, bubbling sea of quantum fluctuations, where pairs of particles and their antiparticles would spontaneously blink into and out of existence. On the subatomic scale, this quantum jitter is normally invisible and fleeting, but during the period of hyper-fast inflation, these tiny fluctuations were stretched across the cosmos faster than they could vanish. The microscopic became macroscopic. A quantum fuzz, smaller than a single atom, was inflated to a size larger than our entire observable universe in a fraction of a second. This process left a permanent stamp on the fabric of reality. Regions of space that were momentarily slightly denser due to this quantum jitter became the warm spots in the cosmic microwave background. Areas that were momentarily less dense became the cool spots. The universe's largest structures, from galaxy clusters to vast cosmic voids, were all seeded by these random, subatomic tremors. The statistical pattern of these fluctuations is a powerful clue. They exhibit a property known as scale invariance. This means the pattern of bumps and dips looks essentially the same whether you examine a large swath of the sky or a tiny patch. It is a fractal-like signature, and it is precisely the pattern predicted by the simplest models of cosmic inflation. This is not a random distribution. It is a specific, predictable outcome of a rapid, exponential expansion. By meticulously mapping these statistical properties, cosmologists can perform a kind of cosmic archaeology, working backward to determine the universe's fundamental ingredients and their precise proportions. The specific characteristics of these seeds tell us exactly how much of the universe is made of ordinary matter. How much is the mysterious dark matter that holds galaxies together? And even how much is the enigmatic dark energy driving the cosmic acceleration? Every galaxy, every star, and every planet is the end result of a gravitational cascade that began with a quantum whisper. The grand cosmic web we see today, with its glittering filaments and immense voids, is the final expression of a blueprint drawn by quantum mechanics in the first trillionth of a second of time. But how do we decode this blueprint to understand the universe's actual recipe? The blueprint encoded in the cosmic microwave background allows us to perform a precise cosmic census, weighing the universe's fundamental ingredients with astonishing accuracy. Detailed analysis of how those ancient temperature ripples evolve and interact with matter reveals a recipe that is both humbling and bizarre. The stunning conclusion is that the ordinary matter we know and love, the atoms that form every star, every planet, and every living thing, accounts for a mere 5% of the total cosmic budget. The universe we can directly see is just the visible tip of a vast, invisible iceberg. The rest is composed of two profound mysteries. About 27% of the cosmos is made of dark matter. This enigmatic substance does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. We only know it is there because of its powerful gravitational pull, which holds spinning galaxies together and bends the path of light itself. Without this dark matter scaffolding, galaxies would have simply flown apart long ago. The largest component, a dominant 68%, is the most puzzling of all: dark energy. This is not a material substance but a repulsive force inherent to the fabric of space, causing the expansion of the universe to accelerate over time. Think of it as a kind of cosmic anti-gravity, pushing galaxies apart from one another with ever-increasing speed. This cosmic budget forces a radical rethinking of our place in the cosmos. Everything that is familiar to us, all the light and life in the universe, is a rare and precious anomaly floating in a sea of darkness. The CMB has given us the numbers, but the true nature of dark matter and dark energy remains one of the greatest unsolved problems in all of physics. With the universe's fundamental composition now laid bare, a deeper architectural question emerges. What is the overall shape of the cosmos these ingredients have built? The geometry of our universe is not a matter of abstract mathematics. It is a physical property, a shape writ large across the cosmos, and the cosmic microwave background holds the definitive proof of its form. The universe, on its largest observable scales, is geometrically flat. This is not flat like a sheet of paper, but flat in the sense of Euclidean geometry, the rules we learn in school. In a flat universe, two parallel laser beams shot across the void will never converge or diverge. They will remain perfectly parallel forever. This flatness arises from an incredibly precise balance that was struck in the universe's earliest moments, a perfect equilibrium between the outward push of expansion and the inward pull of gravity from all the matter and energy contained within the cosmos. This specific density is known as the critical density. If the universe had contained just a bit more matter and energy, its gravity would have caused space to curve back on itself into a closed, spherical shape, destined for a final collapse. If it had contained a bit less, space would curve outward in an open, saddle-like shape, leading to a fate of eternal, runaway expansion. The patterns of hot and cold spots in the CMB act as a cosmic ruler. In a curved universe, these patterns would appear distorted, their apparent sizes warped by the underlying geometry of space itself. But the patterns we see are pristine and undistorted, revealing a universe that is flat to within a margin of error of just 0.4%. This is an astonishing level of fine-tuning. For the universe to be this flat today, its density in the first second of existence must have been tuned to 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a level of precision that is virtually impossible to comprehend. Such perfection does not happen by accident. It is the clearest predicted outcome of cosmic inflation. The theory states that the universe's explosive initial growth spurt would have stretched space so violently that any initial curvature would have been smoothed out, just as inflating a balloon makes its surface appear flatter and flatter from the perspective of a tiny ant on its surface. This geometric flatness has profound implications. It suggests the universe may be truly infinite in extent, with our observable cosmos being just a tiny patch within a limitless whole. It also sets the stage for the long-term evolution that allowed galaxies and life to form, balancing on a razor's edge between collapse and dispersal. Such a perfectly calibrated beginning forces us to ask what other fundamental properties were locked into place during that initial, unimaginable expansion. The evidence for cosmic inflation is written across the sky in the language of the cosmic microwave background. This ancient light provides 3 powerful, interlocking clues that point toward a period of hyper-fast expansion in the universe's first fleeting moments. The first clue is the overwhelming uniformity of the background itself. The temperature of this afterglow is almost exactly the same in every direction we look, a fact that presents a profound puzzle known as the horizon problem. How can regions of the cosmos now on opposite sides of the visible universe be so perfectly synchronized? Without inflation, these regions would never have been in contact, no more than 2 distant islands with no bridge between them. Cosmic inflation solves this by suggesting that the entire observable universe was once a tiny, subatomic patch, where temperature could easily equalize. This patch was then stretched to a size larger than our entire cosmos in a fraction of a second, carrying that initial smoothness across the vast expanse we see today. The second clue is the specific statistical pattern of the tiny temperature ripples. These fluctuations are scale invariant, meaning the pattern of hills and valleys looks statistically identical whether you examine a large swath of sky or a very small one. This is the precise fingerprint predicted by the simplest models of inflation, a signature of quantum jitter magnified to a cosmic scale. The third and final clue is the geometric flatness of the universe. The perfect balance we observe, the razor's edge between expansion and collapse, is a natural outcome of the inflationary process. Imagine the surface of a wrinkled, crumpled balloon. As you inflate it, the surface becomes smoother and flatter. In the same way, the violent expansion of inflation would have stretched any initial curvature of the infant universe into the geometrically flat cosmos we measure today. Together, these three pieces of evidence form a compelling case that our universe did indeed undergo this incredible growth spurt. The CMB data acts as a strict referee, allowing scientists to test and refine different models of inflation, ruling out some and providing support for others. While the direct detection of primordial gravitational waves remains a key goal, the existing evidence strongly suggests that the large-scale structure of our entire reality was forged in that first unimaginable burst of expansion. This dramatic beginning set the cosmic stage, but the real work of building a universe was just about to begin. Before the first stars ignited, the newborn universe was filled with sound. This was not sound as we know it, traveling through air, but a deep, rhythmic pressure wave propagating through the searing hot plasma that filled all of space. In that dense, opaque fluid, photons of light and particles of matter were locked in a tight embrace, creating a medium where compressions and rarefactions could travel as vast, cosmic-scale vibrations. These are the primordial sound waves, or Baryon acoustic oscillations, and their frozen echo is permanently imprinted on the cosmic microwave background. The physics is surprisingly straightforward. Gravity would pull matter inward towards slightly denser regions, but the intense pressure from the trapped radiation would fiercely push back, creating an oscillating cycle of collapse and rebound. This back and forth created a series of spherical sound waves, rippling outward from every overdense seed in the early cosmos. But this cosmic symphony had a final, abrupt note. When the universe cooled enough for atoms to form, the radiation suddenly streamed away, the plasma vanished, and the sound waves instantly froze in place, their progress halted. This moment captured a specific distance that a sound wave could travel from the beginning of time until that instant of liberation. That distance, the sound horizon, became a permanent cosmic ruler etched into the fabric of the universe. We see its signature as a very specific, statistically preferred scale in the map of the CMB's hot and cold spots. If you could average all the fluctuations, you would find a distinct ring of slightly higher temperatures surrounding each of the ancient warm spots, a fossilized imprint of that final, outward pressure wave. This is not just a historical curiosity. That specific scale, about 500,000 light-years across at the time, acts as a fantastically precise standard ruler. Because we know its absolute size from the physics of the early universe, we can use it to measure vast cosmic distances. By observing how this same scale appears in the distribution of galaxies billions of years later, we can trace the expansion history of the universe with incredible precision. The detection of these acoustic peaks in the CMB power spectrum was one of the great triumphs of modern cosmology. It provided stunning confirmation that our mathematical models of the universe's first 400,000 years were correct, down to the finest details. These frozen sound waves are the rhythmic backbone of cosmic structure, a fundamental vibration that set the pattern for where galaxies would eventually form. But this symphony of matter left behind another, more subtle kind of echo, one written not in heat, but in the very direction of the ancient light itself. The frozen sound waves left a permanent mark in the temperature of the ancient light, but they also twisted the light itself. This ninth secret is written in the subtle polarization of the cosmic microwave background. Light, as it travels, can vibrate in specific directions, and this property, called polarization, acts as a second, more refined channel of information from the dawn of time. The mechanism that imprinted this signature was the final act of Thomson scattering, the last time those primordial photons bounced off free electrons in the hot plasma. As the universe cooled and atoms formed, this final scattering event captured the direction of the prevailing motion in the plasma, polarizing the light in the process. This polarization comes in two distinct patterns, much like the different ways you can distort a rubber sheet. The first type, known as E-mode polarization, is a curling pattern that points directly toward or away from the source of a density fluctuation, like the petals of a flower radiating from its center. This pattern was generated by the same sound waves and gravitational pulls that created the temperature variations, and its clear detection provides a powerful, independent confirmation of our entire story of the early universe. The second type, B-mode polarization, is a swirling, curl-like pattern that is far more elusive. This faint signature could be the ultimate prize, as it has two potential sources. One is the weak distorting effect of all the matter, both light and dark, that the CMB light passed through on its 13 billion-year journey to us, bending its path. The other, more profound source would be those primordial gravitational waves, the ripples in spacetime from inflation, which would have twisted the fabric of reality itself as the light was being set free. By meticulously separating these two polarization patterns, cosmologists gain a cleaner, sharper view of the universe's initial conditions. The E-modes help break degeneracies, fine-tuning our measurements of fundamental cosmic ingredients with even greater precision. The hunt for the primordial B-modes, however, is a direct probe of the universe's most violent instant. This polarized light is more than just a fossil. It is a cosmic compass, its subtle twists and turns guiding us through the invisible distribution of matter and pointing directly back to the first tremors of creation. That ancient light has traveled for over 13 billion years to reach our telescopes, but its journey was never a straight line. The path of every cosmic microwave background photon is warped and bent by the gravitational pull of everything it passes. Galaxies, vast clouds of dark matter, and entire clusters act as cosmic lenses, subtly distorting the pristine patterns of hot and cold spots imprinted at the dawn of time. This phenomenon, known as gravitational lensing of the CMB, is the 10th secret hidden within the glow. It is as if we are looking at the universe's baby picture through a sheet of rippled glass. The tiny temperature fluctuations are slightly smeared, their shapes stretched and twisted by the invisible mass that lies between us and the edge of the observable universe. By meticulously measuring this subtle distortion, cosmologists can perform a remarkable feat. They can map the total distribution of matter along the entire line of sight, from the present day all the way back to the moment of recombination. This is an incredibly powerful tool because the vast majority of that matter is the invisible dark matter that neither emits nor absorbs light. CMB lensing allows us to see the unseen, tracing the cosmic scaffolding of dark matter that guides the formation of galaxies. Sophisticated experiments like the Planck satellite and the Atacama Cosmology telescope have used this technique to produce detailed mass maps of the universe. These are not maps of light, but maps of gravity itself, revealing the cosmic web in stunning clarity. This lensing effect also acts as a cosmic history book. By observing how the lensing signal changes when we look at different distances, we can track how these massive structures have grown and evolved over billions of years. This provides a direct test for our theories of gravity and the nature of dark energy, the force accelerating the expansion. A stronger or weaker lensing signal than expected could hint at new physics, perhaps a modification to Einstein's theory of general relativity on the largest scales. Furthermore, this gravitational warping helps us measure the universe's expansion history with even greater accuracy. It breaks key degeneracies in our cosmic models, providing an independent check on the Hubble constant and the overall geometry of space. The CMB is no longer just a static snapshot. Through the subtle art of lensing, it becomes a dynamic probe. Its distorted whispers revealing the growth and distribution of the invisible cosmos that shapes our reality. That ancient light provides a cosmic clock, a way to measure the very rate at which our universe is stretching apart today. This 11th secret is the Hubble constant, a single number that quantifies the current expansion speed of the cosmos. By analyzing the precise scales of the hot and cold spots in the cosmic microwave background, scientists can work backward through the entire history of cosmic expansion. They use the CMB as a fixed starting point, applying our well-tested model of the universe's evolution to predict what the expansion rate should be right now. The result is a highly precise, model-dependent value for the Hubble constant, a cornerstone of our standard model of cosmology. Yet, a fascinating conflict has emerged. When astronomers use other methods to measure the Hubble constant directly in our local universe, by observing the distances and recession speeds of nearby galaxies and supernova, they get a different answer. The local measurements suggest the universe is expanding noticeably faster than the pristine CMB data predicts. This discrepancy is known as the Hubble tension, and it is not a small statistical fluke. It is a persistent, significant gap that has survived years of reanalysis and improved observations. This is not merely a debate over numbers. It is a potential crack in the foundation of modern cosmology. If it is not due to some hidden systematic error in our measurements, then the Hubble tension could be the first real evidence that our standard model is incomplete. It might be pointing towards something profound and unexpected. Perhaps dark energy is not a constant force but is evolving over time, growing stronger. Or maybe there is a new, previously unknown type of neutrino or other relativistic particle that was present in the early universe, subtly altering its expansion history. Some physicists even speculate it could hint at a modification to Einstein's theory of gravity itself on the largest imaginable scales. This single number, derived from the universe's oldest light, has thrown down a gauntlet, challenging our most fundamental understanding of cosmic evolution. Resolving this tension is a primary driver for the next generation of incredibly sensitive observatories, which will map the CMB with even finer detail. They are searching for any subtle anomaly in the ancient patterns that could explain why the young universe and the old universe seem to be telling two different stories about the rate of our cosmic expansion. What other hidden ingredients waiting to be discovered could be altering the tempo of the cosmos? That same ancient light even holds traces of the most elusive particles in existence, the ghostly neutrinos. In the first second of the cosmos, the universe was so dense and hot that trillions upon trillions of these subatomic phantoms were created, streaming freely through the primordial plasma. Neutrinos are famously aloof, barely interacting with normal matter. A single neutrino could pass through a light year of solid lead without a single collision. Yet, their collective presence in the infant universe left a subtle but measurable scar on the cosmic microwave background. Because they were so abundant, neutrinos contributed to the overall energy budget of the early cosmos, acting as a form of radiation. This influenced the expansion rate during those critical first moments, subtly altering the timing of key events like the formation of the first atoms. More importantly, their constant high-speed flight had a specific smoothing effect. As they streamed out from denser regions, they carried energy away with them, effectively wiping out the smallest ripples in the matter distribution. This neutrino damping left a distinct signature in the statistical pattern of the CMB's temperature variations, a slight suppression of fluctuations on the very finest scales. By analyzing this imprint with extreme precision, cosmologists have placed the tightest constraints ever on neutrino properties. The data reveals that the combined mass of all three known types of neutrinos must be extraordinarily small, less than 0.12 electron volts. To grasp how minuscule that is, consider that a single electron, a tiny particle itself, is over 4 million times heavier. This cosmic measurement confirms that neutrinos are astonishingly lightweight, but not entirely massless. Furthermore, the CMB pattern acts as a definitive cosmic census for particle types. It confirms that there were only 3 light, active neutrino species in the early universe. This powerful observation rules out entire classes of theoretical physics models that propose the existence of additional, sterile neutrinos. It is a profound convergence of scales, where the oldest light in the universe provides fundamental insights into the realm of the infinitesimally small, insights that are sometimes impossible to obtain in even the most powerful particle colliders on Earth. The whispers of these cosmic ghosts, frozen in the afterglow, remind us that the story of the largest structures is inextricably linked to the nature of the smallest particles. With the universe's particle content now firmly established, we can use this ancient light to construct a precise chronology, a cosmic clock that marks the key events in the life of our universe. The universe did not remain transparent for long after that first brilliant flash of light. The cosmic microwave background carries a dual memory, chronicling not one but 2 great transformations in the early cosmos. The first was recombination, the moment we have already met when the universe cooled and atoms formed, setting the CMB free. But hundreds of millions of years later, a second, more dramatic upheaval occurred, known as reionization. The cosmos had fallen into a dark age after recombination, a vast sea of neutral hydrogen gas. Then, the first stars and galaxies ignited. Their intense, ultraviolet radiation acted like a cosmic sunrise, blasting apart those neutral hydrogen atoms, stripping electrons from their nuclei once again. This process of reionization flooded the universe with a searing light, burning away the fog and making intergalactic space transparent to high-energy photons for the rest of cosmic history. We can actually see the echo of this second dawn in the CMB. As the first starlight began to reionize the gas, the newly freed electrons scattered the CMB photons one last time. This final, distant encounter imprinted a specific, large-scale pattern onto the light's polarization. By measuring this signature, scientists have determined that this reionization process was well underway by the time the universe was about 500 million years old. This timeline is a crucial bridge. It connects the pristine, simple universe captured in the CMB directly to the later emergence of complex structure, the very first stars switching on to end the cosmic dark ages. It tells us when the lights first came on in the cosmos. How long did it take, from that initial flash of the CMB, for the universe to mature enough to build those first brilliant beacons? That single ancient snapshot allows us to calculate the universe's birthday with astonishing accuracy. The cosmic microwave background reveals a cosmos that is precisely 13.8 billion years old. This number is not a rough guess. It is a precise figure derived by combining the detailed map of the CMB with our robust model of cosmic evolution. By measuring the exact proportions of dark energy, dark matter, and ordinary matter, and by tracing the expansion history backward from that first flash of light to the present day, cosmologists have pinned down this age with an uncertainty of less than 1%. This is the ultimate cosmic clock, ticking all the way back to the singular moment of the Big Bang. But this definitive age also points toward a profound and sobering future. The same data that tells us when the universe began also charts its long-term destiny. The current consensus, driven by the measured dominance of dark energy, is a future of eternal expansion. The universe will not just continue to grow. It will accelerate, with galaxies flying apart from one another at ever-increasing speeds. Over trillions of years, the cosmos will gradually cool and become more and more dilute. Star formation will cease as gas reservoirs are exhausted. Existing stars will burn out, and galaxies will fade to darkness. The universe will become a cold, ever more empty void, a fate often called the heat death. The CMB does more than just predict this likely outcome. It acts as a strict referee for other, more dramatic possibilities. Could dark energy grow stronger over time, eventually tearing apart galaxies, stars, and even atoms themselves in a final cataclysm known as the Big Rip? The patterns in the ancient light tightly constrain how quickly such a scenario could unfold. And for now, the data does not support it. Could the gravitational pull of matter somehow reverse the expansion, leading to a catastrophic Big Crunch? The CMB's measurement of a geometrically flat universe, with too little matter to overcome dark energy, makes this fate highly improbable. Knowing our cosmic lifespan, from a fiery beginning to a cold, dark end, frames our entire existence within a grand, if stark, narrative. It highlights a fleeting epoch of cosmic complexity, a brief window in the universe's long history where light, matter, and life could flourish. This contemplation of an ultimate end inevitably draws our gaze backward, to the very first instant, and forces us to ask what, if anything, came before that beginning. The universe's definitive birth certificate might also contain a faint signature from a time before time. Some of the most intriguing secrets hidden within the cosmic microwave background are its anomalies, features that stubbornly refuse to fit the pristine predictions of our standard model. These are not the tiny temperature ripples that seeded galaxies, but larger, more puzzling asymmetries. One half of the sky appears subtly different from the other, and there is a mysteriously large cold spot that seems improbably vast. While these could be statistical flukes or artifacts of our measurement, a tantalizing possibility is that they are cosmic scars, imprints from a reality that existed before the Big Bang. One speculative theory suggests our universe is cyclical. A previous cosmic era may have collapsed in a big crunch, and the energy of that collapse rebounded into our own Big Bang. The violent dynamics of that transition could have left a bruise on the very fabric of our new universe, a permanent asymmetry frozen into its first light. Another idea, born from the theory of eternal inflation, proposes that our universe is just one bubble in a vast, frothing multiverse. The cold spot could be the imprint of a collision with a neighboring bubble universe in that primordial foam, a cosmic dent from a long-ago encounter with another reality. These concepts are at the furthest frontier of theoretical physics, far from confirmed science. Yet, the very fact that we can use the CMB to test them is a testament to its power. It serves as the ultimate testing ground, a cosmic canvas against which we can paint our wildest ideas about existence and see if they match the data. If even one of these anomalies were ever confirmed as a window into a pre-Big Bang epoch, it would fundamentally rewrite our story of creation. The Big Bang would no longer be a true beginning, but a transition, a turning of the page in a much longer cosmic story. The ancient glow would then be more than a baby picture. It would be a palimpsest, with the faded text of a previous universe still visible beneath the vibrant ink of our own. One of the most profound foundations of modern cosmology is the cosmological principle, the idea that the universe is essentially the same in every direction and from every location. It is the bedrock upon which our entire understanding of the cosmos is built. But what if this foundational assumption is wrong? A strange and persistent feature in the cosmic microwave background directly challenges this core belief. Scientists call it the axis of evil. This is not a malevolent force, but a mysterious statistical alignment where certain large-scale patterns in the ancient glow appear to be correlated with the plane of our own solar system. It is as if the universe's grandest blueprint is subtly tilted, whispering a secret connection to our own local cosmic neighborhood. According to the cosmological principle, this should be impossible. The universe should have no preferred direction, no grand axis that aligns with our insignificant corner of a single galaxy. The fact that we seem to see one is deeply unsettling. Most researchers believe this is likely a statistical fluke, or perhaps an unresolved artifact from how we process the data, a ghost in the machine of our most powerful telescopes. Yet, the axis of evil has proven stubborn. It persists across different analyses and data sets, refusing to be fully explained away. If it is real, the implications are staggering. It could mean that our local environment, the gravitational pull of the Milky Way and its surroundings, casts a far longer shadow than anyone imagined, somehow imprinting itself on the oldest light in the universe. Or more profoundly, it could point to entirely new physics, a fundamental revision of how we understand space and time on the largest scales. This anomaly is a powerful reminder that our standard model of cosmology, for all its stunning successes, is not yet complete. It is these lingering puzzles, these faint whispers of discord in the data, that drive science forward. The investigation of the axis of evil forces cosmologists to be their own most rigorous critics, to question their most basic assumptions, and to remain open to the possibility that the cosmos is even stranger and more wondrous than we have yet dared to believe. Another stubborn puzzle is waiting in the southern sky. It is called the cold spot, a region of the cosmic microwave background that is chillingly colder than the standard temperature ripples should allow. This is not a minor statistical blip, but a vast and profound coolness that stretches across a huge swath of the cosmos. The most straightforward explanation points to a cosmic emptiness. If a truly immense supervoid, a bubble of relatively empty space, lies directly in our line of sight to this part of the CMB, it could create this cold patch through a phenomenon called the integrated Sachs-Wolf effect. Here is how it works. As a CMB photon travels toward us through the expanding universe, it must climb in and out of the gravitational wells of galaxies and dark matter. Normally, the energy lost climbing into a well is regained when it climbs out. But if that well is stretched and weakened by the accelerating expansion of dark energy while the photon is inside it, the photon does not get all its energy back. It emerges slightly cooler. A vast supervoid would be a shallow but enormous gravitational hill, and crossing it would leave a whole collection of photons noticeably colder. The mystery deepens because searches for a supervoid large enough and empty enough to cause such extreme cooling have been inconclusive. The observed coldness seems too intense for the supervoids we have found. This mismatch has opened the door to far more exotic possibilities. Could the cold spot be a cosmic bruise, the imprint of a collision with another bubble universe during the inflationary epoch? In the theory of eternal inflation, our universe is one bubble in a vast, foaming multiverse. A collision with a neighboring bubble could have left a permanent scar on our cosmos, a specific texture of cooler temperature frozen into the CMB. While most cosmologists still favor a purely astrophysical explanation, perhaps involving a complex combination of smaller voids, the cold spot refuses to be neatly solved. It stands as a powerful testament to how a single, stubborn anomaly can force science to its limits, compelling us to question our assumptions and daring us to imagine realities beyond our own. This enigmatic cold patch does more than challenge our models. It invites us to trace the path of the ancient light itself, to map the immense and shadowy structures that fill the cosmic space between our present and the primordial past. The cosmic afterglow serves as the ultimate testing ground for gravity itself. While Einstein's theory of general relativity has passed every test for a century, the profound mysteries of dark matter and dark energy have prompted physicists to ask a radical question. What if our understanding of gravity is incomplete on the largest cosmic scales? The patterns in the cosmic microwave background provide a definitive answer. Modified gravity theories propose that we can explain the universe's accelerated expansion and the motions of galaxies not with invisible substances, but by tweaking the laws of gravity themselves. These theories make very specific predictions about how the universe's large-scale structure should grow. They forecast how quickly galaxy clusters should form and how the gravitational potential wells from dark matter should evolve, all of which leave a unique fingerprint on the subtle statistics of the CMB's temperature and polarization patterns. When we compare these predictions to the exquisitely precise data from satellites like Planck, the Standard Model, with its combination of general relativity, dark matter, and dark energy, emerges victorious. The evidence overwhelmingly supports the existence of dark matter as a particle and dark energy as a component of space. The CMB data has effectively ruled out many of the simplest and most popular modified gravity proposals. This is not the end of the story, however. It is a refinement. The very constraints provided by the CMB are now guiding theorists, showing them which avenues are still possible and which are definitively closed. The next generation of CMB observatories will map the sky with even greater fidelity, searching for the tiniest of deviations that could signal a crack in our current understanding. A confirmed discrepancy would be a revolution, pointing the way toward a new theory of gravity that unites the cosmic and the quantum realms. This relentless testing underscores a profound truth. The ancient light is more than a relic. It is a fundamental physics laboratory, one that constrains the very nature of force and spacetime. As we push this investigation to its limits, we are inevitably drawn to one of the most speculative and thrilling possibilities. Could the true nature of gravity be hidden in dimensions of space that lie forever beyond our perception? The fabric of spacetime may possess a hidden architecture, with dimensions folded into shapes too small for our senses to perceive. This is not science fiction, but a serious proposal from theories like string theory that attempt to unite gravity with quantum mechanics. To make this union work, the mathematics often requires more than the three spatial dimensions of length, width, and height that define our everyday reality. There could be 6 or 7 additional dimensions, curled up into a microscopic labyrinth at every single point in space. If these extra dimensions exist, their ghostly influence could have left a faint signature on the universe's first light. During the violent expansion of cosmic inflation, the primordial gravitational waves rippling through the cosmos would have propagated through all dimensions, not just the 3 we see. The presence of these hidden realms would have subtly altered how those spacetime ripples traveled, changing the specific swirl-like pattern, the B-mode polarization, we expect to find imprinted on the CMB. It would be like listening to a bell ring in an empty room versus a room filled with intricate, unseen furniture. The echo would be different. Furthermore, the very statistical properties of the hot and cold spots, the specific way their sizes and temperatures are distributed, could be minutely skewed by the gravitational effects leaking from these compact dimensions. The exquisitely precise values we measure for the cosmic ingredients, the amounts of dark matter and dark energy, might also be shifted by this hidden geometry. So far, the cosmic microwave background shows no definitive trace of these extra dimensions. The data from Planck and other observatories has acted like a cosmic sieve, ruling out many theoretical models and placing tight constraints on the possible size and shape of these hypothetical realms. They must be smaller than a certain scale, or else their effects would have been visible. This relentless search beautifully ties the largest observable canvas, the ancient sky, to the most ambitious quest in physics, the theory of everything. The CMB becomes a bridge, connecting the cosmic to the quantum, testing ideas that are otherwise beyond the reach of any particle accelerator on Earth. This pursuit forces a profound question about the underlying nature of our reality. Is the universe fundamentally simple, its elegant laws written in a language of higher dimensional geometry, or is its apparent complexity the ultimate truth? The universe's oldest light is a perfect example of cosmic disorder. This faint glow is a nearly ideal blackbody, a state of remarkably high entropy. In the language of physics, entropy is a measure of disorder or randomness, and a high-entropy system is one that has settled into a stable, uniform, and thoroughly mixed state, like a cup of coffee that has cooled to room temperature. The fact that the cosmic microwave background is so perfectly smooth and thermalized tells us the universe has already reached a state of very high disorder. This presents a profound puzzle, because for the complex structures we see around us to ever form, the universe must have started in a condition of incredibly low entropy. Think of a new deck of cards, perfectly ordered by suit and value. That is a state of low entropy. Shuffle that deck thoroughly, and you create a state of high entropy, a random sequence. Our observable universe is that shuffled deck. The mystery is why it began as an ordered one. The low entropy past was the necessary starting gun for the arrow of time itself, allowing for the formation of stars, planets, and life. Without that initial order, gravity could never have begun its work of pulling matter together. The tiny fluctuations in the CMB are the subtle fingerprints of that initial low entropy state. Scientists can even analyze these patterns in terms of information theory, treating each hot and cold spot as a bit of data. The specific arrangement of these fluctuations holds clues about the total information content of the observable universe and the precise nature of its low entropy beginnings. Some theories push this idea to its limit, exploring whether the universe, for all its apparent complexity, might actually be in a state of maximum entropy given its total size and energy. This seems counterintuitive, but if gravity is considered, a black hole is the object with the highest possible entropy for a given volume. From this perspective, our vast, expanding cosmos could be the highest entropy state available. This line of thinking leads directly to the holographic principle, the radical idea that all the information describing our three-dimensional reality might be encoded on a two-dimensional surface at its boundary, much like a hologram. The cosmic microwave background, that faint whisper from the dawn of time, could be one of our primary windows into understanding this cosmic data storage. Its patterns are not just a map of temperature, but a fundamental record of the universe's initial information budget, a thermodynamic story written in the cold glow of empty space. The universe's first quantum whisper has grown into a test of reality's deepest nature. Those delicate patterns in the cosmic microwave background are now being used to perform a cosmic-scale Bell test, probing the fundamental rules of quantum mechanics across the entire sky. In laboratory experiments, a Bell test checks whether particles are connected through spooky action at a distance, a phenomenon called quantum entanglement, or if their behavior is governed by a more mundane, local reality. The correlations between hot and cold spots on opposite sides of the CMB sky serve as the data for this grand experiment. Incredibly, the way these distant regions are linked strongly suggests that quantum entanglement was operating across distances that should have been causally disconnected, regions that had no time for light or information to travel between them. This bizarre connectivity is a direct prediction of cosmic inflation. The entire observable universe was once a microscopic quantum system where every part was in contact with every other part. Inflation then stretched these intrinsic quantum connections to astronomical sizes, freezing them into the temperature variations we observe today. While the interpretation is philosophically complex, as the quantum fluctuations became the classical seeds for galaxies, the observational evidence is compelling. The cosmos itself becomes a laboratory, testing quantum principles on a scale no human experiment could ever replicate. This profound link demonstrates that the rules governing the smallest particles are inextricably woven into the fabric of the largest structures, revealing a unity between the microcosm and the macrocosm. If the universe's vast expanse can be traced back to a quantum beginning, it forces us to consider an even more radical idea. Could our three-dimensional reality, with all its galaxies and its ancient light, be a projection from a simpler, two-dimensional surface, like a cosmic hologram? This ancient light might be a cosmic hologram, a two-dimensional projection of a deeper reality. The 22nd secret hidden in the cosmic microwave background is the search for clues that our universe is fundamentally holographic. This mind-bending idea draws its inspiration from the physics of black holes. When matter falls into a black hole, it seems the information it contains is not lost forever. Instead, theoretical work suggests that all the information about what fell in becomes encoded on the black hole's event horizon, its two-dimensional boundary surface. The holographic principle boldly applies this same logic to the entire cosmos. It proposes that our seemingly three-dimensional universe, with all its galaxies, stars, and planets, could be a projection from a two-dimensional surface at the edge of space. The sky we observe, including the map of the CMB, might be that very screen. According to this radical view, the fluctuations in the ancient light are not just temperature variations. They are pixels. Each tiny hot and cold spot could be a piece of data, a bit of information emerging from a cosmic code written on the spherical boundary of our observable universe. Scientists have meticulously analyzed the statistical properties of the CMB's patterns, searching for a specific kind of anomaly that would be the signature of this holographic encoding. They are looking for a subtle suppression of certain fluctuations on the largest scales, a statistical fingerprint predicted by some holographic models. So far, the search has not yielded a conclusive detection. The standard model of cosmology still provides the best fit to the exquisite data. Yet, the very fact that we can use this ancient glow to test such a profound and speculative idea is remarkable. It transforms the CMB into a testing ground for the nature of reality itself. A confirmed holographic signature would mean that space is not fundamental. The three-dimensional volume we inhabit and move through would be an emergent illusion, a holographic movie playing out on a distant, two-dimensional cosmic film. This challenges our most basic intuitions about depth, distance, and existence. If our entire universe is a projection from a lower dimensional reality, it forces a profound question. Could the screen upon which our reality is written be just one of countless projections in a far vaster, more complex multiverse? The concept of a multiverse emerges not as a fantasy, but as a direct and startling consequence of the theory that best explains our own universe. The same cosmic inflation that smoothed and flattened our cosmos is thought to be an eternal process, constantly spawning new bubble universes within an unfathomably vast meta-realm. Each of these bubbles could have its own unique set of physical laws and fundamental constants, a different cosmic recipe where matter might not exist, or gravity could be repulsive. Our universe, with its specific, life-permitting parameters, would then be just one rare island in an infinite archipelago of realities. While we cannot travel to these other realms, the cosmic microwave background might hold the first indirect proof of their existence. The most tantalizing evidence would be a specific kind of bruise on the ancient sky, a pattern left by a long-ago collision with a neighboring bubble universe as both expanded. Such a cosmic crash would have sent shockwaves through the fabric of our infant cosmos, potentially leaving an odd, circular pattern of temperature variation imprinted on the CMB, a fossilized impact crater on the largest possible scale. This is one proposed explanation for anomalies like the mysterious cold spot, a vast region of unexpected chill that defies simpler explanations. Furthermore, the multiverse offers a profound answer to one of cosmology's deepest questions. Why are the constants of nature so perfectly fine-tuned for the emergence of life? The force of dark energy, for instance, is calibrated with unbelievable precision. If it were slightly stronger, the universe would have blown itself apart before galaxies could form. If it were weaker, gravity would have caused a swift collapse. In a multiverse, there is no mystery. An infinite number of universes exist with all possible values, and we simply find ourselves in one of the rare, lucky ones where the numbers allow for stars, planets, and observers. This idea, known as the anthropic principle, shifts the question from why our universe is special to the statistical inevitability that some universe would be. Currently, the multiverse remains a speculative framework, a breathtaking possibility not yet confirmed by hard data. No definitive collision signature has been found, and other explanations for cosmic anomalies are still possible. Yet, the very fact that we can use the ancient light of the CMB to test such a radical concept demonstrates how far cosmology has come. It expands our perspective from a single cosmic story to a potentially infinite ensemble of narratives, challenging the very definition of reality. This ultimate expansion of our cosmic view brings us to the final frontier, the future missions designed to listen ever more closely to the universe's first and most important message. Our cosmic fossil is about to reveal its secrets with a new and breathtaking clarity. The next generation of observatories is already under construction, designed to listen to the ancient light with a sensitivity we have never before possessed. Projects like the Simons Observatory in the high Chilean desert and the ambitious CMB-S4, a network of ultra-sensitive telescopes at the South Pole, will map the sky with revolutionary precision. Their primary goal is to hunt for the holy grail of cosmology, the swirling B-mode polarization pattern of primordial gravitational waves. They will either detect this faint echo from inflation or rule out entire classes of inflationary models, forcing a dramatic rethink of the universe's first instant. These instruments will also act as cosmic scales, measuring the total mass of neutrinos with such accuracy that they might finally tell us if these ghostly particles have a tiny but real weight. Every subtle statistical anomaly, every potential deviation from the standard model, will be scrutinized for signs of new physics. We will see the dark matter web through CMB lensing with the sharpness of a high-definition photograph, tracing its evolution through cosmic time. The future, however, lies not in one telescope alone, but in a grand synthesis. The data from these CMB powerhouses will be combined with the emerging maps from gravitational wave observatories and massive galaxy surveys. This multi-messenger approach will weave together a unified cosmic picture, correlating the distribution of matter seen through gravity with the primordial blueprint of the CMB. This ancient glow, the first light of the cosmos, will remain our most vital portal to the beginning of everything, ensuring that for decades to come, it continues to whisper the universe's deepest truths to those who know how to listen. These cosmic revelations bring us face to face with the great unknowns that still define modern physics. We have mapped the ancient light with stunning precision, yet its deepest messages concern the profound mysteries we have yet to solve. We still do not know what dark matter actually is. Is it a sea of undiscovered particles, or something even more exotic? The nature of dark energy is even more baffling. Is it a constant property of the vacuum of space, or a dynamic force that has changed over the lifetime of the cosmos? The theory of cosmic inflation is our best story for the beginning, but we still do not know what field or energy caused that explosive expansion. Was it a unique event or part of a much larger, eternal process? Even the beautiful data from the CMB is not perfectly clean. The axis of evil, the cold spot, and other statistical anomalies linger at the edge of our maps. Are these simply cosmic illusions, the result of our limited perspective? Or are they genuine cracks in our standard model, whispering of physics beyond anything we have yet conceived? The journey from a smooth, hot plasma to the intricate cosmic web of galaxies is a story we understand in broad strokes, but the fine details of how gravity sculpted the first structures remain an active and vibrant area of research. Each of these unanswered questions is not a failure of science, but a beacon. They are the very reason we build more powerful telescopes and push our theoretical models to their limits. The cosmic microwave background has given us the ultimate foundation, a set of unshakable facts upon which to build. Now it challenges us to go further. It transforms from a fossilized snapshot into a dynamic guidepost, pointing toward the next great frontiers of discovery. The universe is not a puzzle we have nearly solved. It is a conversation that has just begun, and its oldest light continues to ask the most profound questions. Our journey through the whispers of the cosmic microwave background has revealed a universe born from a quantum whisper, its entire history written in a faint, cold glow. We have traced the path from a searing, opaque dawn to the clear, structured cosmos we inhabit today. This ancient light confirmed the violent birth of the Big Bang and mapped the gravitational seeds for every galaxy. It forced us to accept a cosmos dominated by invisible dark matter and a repulsive dark energy, while its geometric flatness pointed to a dramatic inflationary beginning. We have used it as a cosmic laboratory to test gravity, to weigh ghostly neutrinos, and to probe the very nature of reality, from quantum entanglement to the holographic principle. The cosmic microwave background is far more than a fossil. It is a testament to human curiosity, a monument to our relentless drive to decode the universe's deepest messages. The great revelations of the last decades have not closed the book on cosmology. Instead, they have flung the doors wide open to even grander mysteries. We still do not know what dark matter is. The true nature of dark energy remains one of the most profound puzzles in all of science. The anomalies in the map, from the axis of evil to the cold spot, continue to challenge our assumptions. These are not failures, but beacons guiding the next generation of explorers. This story invites you to look up at the night sky with a new understanding. That vast, silent expanse is not empty. It is filled with the faded echo of creation, a microwave hum that holds the entire story of everything, from the first instant to the distant future. Which of these cosmic secrets has reshaped your view of the universe the most? Share your thoughts in the comments, and join us as we continue our journey into the heart of space's greatest